Hi guys, let's begin our study of organic chemistry by reviewing some basic atomic structure. I'll be going through the handout here, our outline as usual. And so let's begin by taking a look at the basic components of the atom: protons, neutrons, electrons, etc. Now you have the handout with you. You'll see I'll just move along the handout. I'll use my whiteboard here. So let's begin maybe just with carbon, yeah? And atomic number of carbon is, so we need a periodic table, right? Everybody should have a periodic table. There is one in the very back of your workbook, the course workbook. But the atomic number of carbon is 6, usually written as a subscript, although not always, because any carbon is 6. And then we can have a mass number. And so for this isotope of carbon, we can ask how many protons. So protons here, and hopefully my whiteboard is showing up good on the video here. Number of protons for this isotope equals 6, yeah. What about number of neutrons? That would be, well, protons comes from the atomic number, right? Neutrons, protons plus neutrons equals the mass number, right? So it's really the difference in the two. So the neutrons here is also 6. And then number of electrons. Now electrons can vary. We could have ions, but assuming this is a neutral carbon atom, it would have 6 electrons. Because if it's neutral, the electrons and the protons, of course, equal, and so it's 6 and 6 there. 6 plus 6 here equals 12. And we see for this isotope we have 666. All right. Well, what about another isotope? We could do, what about carbon 13? Okay. Now note, I do not need to write the 6 because any carbon is going to have an atomic number of 6. What's the difference in carbon 13? This would be, I should have set this up and come across here so we can put the numbers here. Protons, of course, is 6. Any carbon is 6 protons, right? That's that 6 number that is always there by default. Number of neutrons. Well, the difference in these two is 7. So this isotope, now we have two different isotopes. What's the definition of isotopes? They vary by number of neutrons. And then electrons equal, well, again, assuming it's neutral, it would be 6. We also could have another isotope of carbon, carbon 14, C14, and this would be, well, of course it's carbon, so it's protons is 6, but neutrons would be 8, because 8 and 6 needs to equal 14, and then of course if it's neutral, then electrons would equal 6. 3 isotopes of carbon, they only vary by number of neutrons. Again, electrons can vary if we start dealing with ions. Okay. These are sort of the 3 natural isotopes of carbon. Natural meaning you'll find them in nature. Carbon 12 is about 99% abundance. Okay, we're showing up here okay. Carbon-13 is about 1% abundance. And carbon-14, well, if that's 100%, but I rounded those off. I mean, this is actually a little bit less than 1, I believe, but I've rounded these off. Carbon-14 is trace amounts, very small amounts, but there are trace amounts present in any natural sample that contains carbon. Your body contains trace amounts of carbon-14 in your DNA, any carbon-based molecule. Now, carbon-12 is the most abundant. Carbon-13 is very important when in organic 2 we do carbon-13 NMR. When you do NMR of carbon, you're only doing it on the carbon-13 isotope. Carbon-12 is not NMR active. Carbon-14 is important because it's radioactive. And because of that, and because of the very long half-life, it's used for carbon dating. Now that's not a new dating app. That is a method which hopefully you've heard of, perhaps, for like dating old fossils, dinosaur bones, etc. Because when the dinosaur died, it no longer took any more carbon-14. And at that point, the carbon-14 in the dinosaur body started decaying. And scientists, we can determine the amount of decay to determine how long the dinosaur, since it has lived. Okay, those are the 3 natural carbon isotopes. There are others, and if you look up on Wikipedia and do carbon isotopes, you'll see many others. The others, though, are man-made. One example is carbon-11. Carbon-11 is also radioactive, but it's man-made. And you should know how many neutrons it has. Now, in the handout, I actually show you a compound which contains carbon-11. Okay, so it's indicated by the 11 superscript, where otherwise the carbons would be shown with no superscript and they're shown as line bond. But this one is shown specifically. It's a synthetic compound which also contains a man-made element, isotope. And carbon-11 is a positron emitter. That's the way it decays, radioactive decay. And the positron that it emits can be used to create an image. Lots of innovation, ingenuity here, science. And the image can be the type of image it creates is called a PET image, a positron emitting topography image. And PET imaging is used, one example of how it's used is to image the brain when trying to determine the prevalence of Alzheimer's disease. And over here is a PET image of the brain that is normal, a normal brain. And this is a PET image of a brain which indicates Alzheimer's. Now, you would have to look into what the colors mean, but ultimately the colors are indicative of disease there. So, very innovative use of an organic molecule, beautiful organic molecule here called Pittsburgh Compound B. It was, I believe, created, first prepared at the University of Pittsburgh. I think it was the second example. That's where the B comes from. You can look this up on Wikipedia. But it is an example of a compound that contains a carbon-11 isotope, a man-made isotope of carbon. Now, there are also isotopes of hydrogen. And on the back of the handout, I discussed those. Now, the isotopes of hydrogen actually get their own names, and that's unique. All the other elements typically go by something like carbon-13 or maybe tellurium-126, but for hydrogen, the isotopes get their own names. Deuterium is a non-radioactive isotope of hydrogen which has 1 neutron. And so while the atomic number is 1, the mass number is actually 2. So it could be called H2, but instead it's called deuterium. Now we'll see deuterium a good bit throughout the course. Well, I won't say a good bit, but occasionally throughout the course. So you need to be familiar with it. I can also note that deuterium is being used more and more in drugs. And below are a couple of examples. This is dextromethorphan. It's used as a decongestant. But you see the CH3 group here, the methyl group, the hydrogens of the methyl group have been replaced with 3 deuteriums. And so this is a deuterium modified drug. And there's lots of reasons why you might want to replace deuterium in a drug. In this particular case, it leads to improved stability of the drug in vivo. So you can read more about that if you're interested. But it's an application of using the deuterium isotope in drug development. Now there is another isotope of hydrogen called tritium. Now tritium has, if you can tell here, 2 neutrons. Of course, 1 proton plus 2 neutrons equals 3. And that's kind of where the tri comes from, and it's called tritium. Now tritium is radioactive. Tritium used to be used a good bit at the Savannah River site, particularly back in sort of the original days, 1950s, 1960s. I don't believe it's used much out there anymore. If you'd like to know why it's used, and it's you would need to look into that, and you could find some information on your own. What I'm doing here is pointing out the names of the 2 additional isotopes of hydrogen and giving you some examples of their use. Okay. Electron configuration. Well, let's look at carbon. You should know from Gen Chem. What do we have here for carbon? Don't we have a 1s? What's next? What's next? A 2s? And then a 2p? And the p, we know we have 3 p orbitals. Carbon being in the second shell. This is as far up as we go, and the second shell consists of both the s orbital and 3 p orbitals. Now valence electrons. How many valence electrons does carbon have? Well, 4. And you see that from the periodic table. Carbon is in group 4, indicative of valence electrons. We can put our electrons in using our standard principles: off-ball principle, Pauli exclusion principle, Hund's rule: 1 electron, 2 electrons, 3 electrons, 4 electrons. But that's valence electrons. Valence electrons is 4. Total electrons though is 6, right? Group 4, that's valence electrons. We need total electrons, yeah? Total electrons, like we said up here several times, is 6. I thought we needed to keep going here. That's going to give us another one here. And then we get, well, we don't pair up here. Hund's rule, right? We fill degenerate orbitals. Degenerate, that is, they have the same energy. We can show an energy progression here. Now we see we have our 6 total electrons. This here would be the valence electrons, and there's 4 there. 4 valence electrons. Outer shell electrons. These are the electrons which we will use when we start doing bonding. The 2 subshell electrons, we'll never do anything with those. So typically we'll only talk about carbon having 4 valence electrons. Now this is ground state configuration. All right. Once we start doing bonding, this is going to be modified. But the core understanding, core principles are here though. That is s orbital, 3p orbitals, and we'll build off of that as we do bonding in organic chemistry. Now, what about the shapes of these orbitals? Types of orbitals. Of course, an s orbital is spherical, like a volleyball, with the nucleus in the middle. And the p orbital is dumbbell shaped, with the nucleus there. There's actually a node there, right? No electron density as we approach the nucleus. So you should be familiar with those shapes from your Gen Chem. Now, of course, once we do hybridization, we'll blend these together and we'll create hybrid orbitals. And they'll have a little bit different shape. But to understand the new shape we get, you have to start by understanding the original shapes, and we'll go from there. So again, this is largely review, but it serves as the foundation for moving forward and further developing our knowledge and the bonding theory. So that's one of the reasons we call certain courses foundational courses. They set the foundation, and so your prereq knowledge sets the foundation for you to move on and to build upon that knowledge. So, pull out your Gen Chem book, make sure you review your atomic structure. Next, bonding. Bonding. Definition. Well, we'll develop a definition as we move along. We're doing covalent bonding. All right. Ultimately, a covalent bond comes from sharing of 2 electrons. Simplest, what if we have a hydrogen? Of course, a hydrogen just has 1 electron, and we can just show that as a dot there. Simplistic. 1 electron for hydrogen. If we were doing carbon, we would do, well, we're showing valence electrons. Of course, the 1 electron of H is a valence electron. For carbon, though, we would have 4 valence electrons, and we would show 4 dots. So H, we have 1. What if there was another H sort of hanging around in chemistry land? And these 2 could come together and magically create a bond, which would be 2 electrons between the hydrogens. And when we say hydrogens, I'm referring to the nuclei. Of course, the electrons, protons and neutrons are in the nucleus, right? And then the electrons are extranuclear, outside the nucleus. So the H represents the nucleus, the electrons are outside the nucleus, but they can sort of team up and create a 2-electron covalent bond. Now, where we typically indicate this with a dash, and there you go. I shouldn't have circled it. It's not an orbital. I just circled it to circle it. There's your magical covalent bond between the two H nuclei. Very simplistic. An entire course could be taught around what's going on here. All right? Let's keep it simple. 2 electrons coming together to make a shared 2-electron covalent bond. We'll build upon that definition. One thing we can note is, why would it want to do this? When we do covalent bonding, the nucleus then gets to count both electrons. Well, let's look here. We got an orbital. What, an S, right? You should know that's an S. Why? Yeah, okay, think about it. But then the other H, let's see if we can do this. These orbitals come together. Okay. It's really orbital overlap, right? What type of orbitals? S orbital overlap. And we could almost put the 2 electrons sort of here in the middle. I'm messing it up a little bit here. But basically, once this magical bond occurs, now the nucleus gets to count both electrons, and now the outer shell of hydrogen is now filled through sharing, and both H's have a duet, is the terminology. All right. Now, we could take time. Again, usually I would not take time. You can fast forward if you like, but if you like the extra little tidbits, of course, if we're dealing with a 1s orbital, the H, that's all it is. It's got 1s. It's got 1 electron. All right? But if we want to fill this outer shell, that's it. You got to bring in 1 more electron. We can bring in that by, when I do this, I'll bring in the electron and I'll say H. I could have showed an E, but bringing in that extra electron, it now has 2 electrons. And the outer shell is filled. And 2 electrons is the duet. That's where the duet comes from. Bonding fills the outer shell of the hydrogen nucleus. Again, very simplistic. But let's move to carbon and let's advance the discussion. Let's over here, noble gas configuration. Yeah, well, if we go back, we can mention that hydrogen now has the configuration of what? Helium. All right, the noble gas, because helium has 2 electrons in the 1s orbital. Now, octet rule we'll see when we talk about carbon. Okay. Let's kind of set this up. I'm going to do carbon. Maybe I should turn the page here, make it broader. We'll see how it goes. Carbon. Well, how many valence electrons? Well, the answer is 4. And what we can do is we can put the 4 electrons around the carbons like this, 4 valence electrons, and now we can ask how many bonds do we need? Well, if you think about it, back over here, hydrogen needed 1 bond to fill this orbital. Each bond you make gets you an extra electron. Keep that in mind. Okay? How many electrons does carbon need to fill the orbital? Well, remember the ground state configuration. We'll go back and forth here. Right here. How many electrons are needed? We need one there, and two here. We need 4. Then the second shell will be filled. Basically, these 4 we can team up. If we bring in an electron here, now I'm going to do here X. That's an electron. Make a bond. Well, let's do this. Let's say the X is the electron from an H. So the carbon electron teamed up with an H electron to make a 2-electron covalent bond. Okay, but there's electrons remaining on this carbon. We can bring in another H, make a covalent bond, bring in another H, make a 3rd covalent bond, and bring in another H and its electron and make a 4th covalent bond. But now, see, carbon gets to count all these new electrons as its own when we do covalent bonding. And now there's 2, 4, 6, 8. Carbon has an octet of electrons around it. And if you remember, we needed 8 total to fill the second shell, and so now we see that this shell would be filled with those 8 electrons. This represents standard bonding for carbon, and we can note that. What is standard bonding? 4 bonds and 0 lone pairs. Okay? Standard bonding for carbon. What's after carbon on the periodic table? Nitrogen. Okay, let's go to nitrogen. How many valence electrons? 5. 1, 2, 3, 4. Now we start teaming up. 5. Why did I only go around 4 and then start teaming up? Well, really when I go around, I'm dealing with the 4 orbitals. Okay? These 4 valence orbitals. Those are the ones, they can hold the electrons. Nitrogen is also second shell. It has 4 valence orbitals. I filled them each with 1, and then I started pairing up. Now, 5 valence electrons. How many bonds do we need to make? 3. We can bring in an H with its electron, an H with its electron, and an H with its electron. And we can get what is actually a known stable compound. By the way, back over here, we should have maybe cleaned this up, and instead of having the 2 electrons there, just made it a dash, right? And we could have shown that like that. And of course, we could have just condensed that down and said CH4. This is a molecule. This is known as methane. It's an alkane, 1-carbon alkane, the simplest of alkanes. And you should be starting to look at the nomenclature video. So that's why it'd be CH4, and you're not going to see something like CH5. Carbon just needs to make 4 bonds. Standard bonding, 4 bonds, 0 lone pairs. Now something like this, or CH3, may be possible if we start having ions. We'll get to that. So, carbon has an octet. Nitrogen has an octet. 2, 4, 6, 8. All right. And the octet rule is very important for one of the things you want to make sure you have when you're looking for good bonding, standard bonding for an atom. So this is common bonding for nitrogen. What is that? It's actually 3 bonds and 1 lone pair. Because we have a lone pair of electrons. And I designate that, abbreviate that as LP. Of course, this would be written like this if we want to use the dash for the 2 electron covalent bonds. And then we just show the lone pair like that. And we can show it condensed. Very often the lone pair is not shown when you condense it down. Sometimes it's not even shown when it's a structure, but you got to know it's there. And if we are asked to officially draw a structure, we need to include lone pairs. And this is, you may know, ammonia. And these two are actually both gases. After nitrogen would be oxygen. How many valence electrons? Hopefully you see that that's 6, and we can come around 1, 2, 3, 4. Now let's start pairing up 5, 6. And we see we need 2 more electrons. That's going to come from bonding. And we can come in with an H. By the way, we could come in with a carbon or any other atom. I'm using H's because the H only has 1 electron and we don't have to deal with anything else around the H. Come in with the H and it's 1 electron. Come in with another H and it's 1 electron. And there we go. Now the oxygen has an octet. 2, 4, 6, 8. Each hydrogen has a duet. The H has 2, because remember, we get to count these 2 electrons towards the H, but we also get to count them for the oxygen. There's your, and that is standard bonding for oxygen, and that is 2 bonds and 2 lone pairs. And of course this is dihydrogen oxide. Of course you know that as water. H2O, right? And I'm not going to worry about bond angles right now. We'll get to that. These bond angles are actually not correct. What's after oxygen on the periodic table? That would be fluorine. Alright, make sure you know how to spell it. It's often misspelled. 7 valence electrons. It's in group 7. 1, 2, 3, 4, 5, 6, 7. How many covalent bonds can it make? And does it need to make to become a happy camper? To become like the noble gas after fluorine neon, it needs 1 more electron. If we're doing covalent bonding, that would come from some other atom willing to share. And if we share an H, we have now a good compound. The F has 2, 4, 6, 8, an octet, and the H has a duet as we want. And we see standard bonding for fluorine, and that would be 1 bond and 3 lone pairs. And this is just HF. Alright. Let's show the lone pairs, make it official. 3 lone pairs. Of course, if you want to just show it condensed, it's often just written like that. Alright. So I'm showing standard bonding here for the second row elements that are most commonly seen, particularly in organic chemistry. But this also applies to elements underneath these. For example, sulfur. What's common bonding for sulfur? Okay, well guess what? It's 2 bonds, 2 lone pairs. For example, you can have H2S. We can also build larger compounds. We can have, well, what's standard bonding for carbon? 4 bonds and 0 lone pairs. We do all H's. Alright, there's your 4 bonds around carbon. There's your 2 bonds to sulfur. What's missing? Well, 2 lone pairs. And we can get to larger and larger structures. But again, elements that are underneath these, we have similar periodic trends. Of course, like with HF, HCl is much more common. But it's going to be just like that. It's going to be 3 bonds and 3 lone pairs, 1 bond. Okay. Of course, what's your common name of the group 7 elements? Anybody? General name of those elements? Halogens, right? That term you should know because it's so common. The oxygen, those are called chalcogens. But I don't expect you to know that because that term is rarely used, and I don't even know if I know the name for the others. But halogens certainly. Okay, common bonding, octet rule. By the way, these here, okay, these structures here in particular, these are our Lewis structures. Okay, that's where we show the bonding electrons as, or the covalent bond is dashes, and then we also show lone pairs. All right, you must show lone pairs if asked for a formal Lewis structure. Now, if you're just hanging around on a Saturday afternoon talking to your buddies about, you know, ammonia or some other compound, you might often not show the lone pairs. But you need to know they're there, right? Yes. Okay, let's see what we've done here. Let's see what we've done. Lewis structures, important considerations. Okay, please read. Duet for H. Oh, expanded octets. Okay, for example, sulfur. Sulfur does do standard bonding just like oxygen, but because sulfur has d orbitals, and any atom that does have d orbitals, it can have sort of expanded octet bonding. For example, you will see sulfuric acid drawn like this. Now, of course, you can put lone pairs there. Oxygen has standard bonding. All right, 2 bonds and 2 lone pairs, 2 bonds and 2 lone pairs, 2 bonds, double bond, that's 2 bonds though, 2 lone pairs, 2 bonds, 2 lone pairs, all standard. But look at the sulfur. That's not standard. That's not 2 bonds, 2 lone pairs. How many electrons around this sulfur? 2, 4, 6, 8, 10, 12. Okay, 12 electrons. That's more than 8. That's called an expanded octet. That's possible because the sulfur is using d orbitals. All the other elements we talked about, we're just using the S and the P because those are just second shell. I mean, not second shell, second row. But sulfur is in the 3rd row. Brings in d orbitals. Okay. And any, okay, charges. Once we start looking at charged atoms, ions, you need to also show charges with a Lewis structure. If you don't show appropriate charge when it's there, your Lewis structure will not be fully correct. Now once we start talking about charges, we'll see that for organic chemistry and the common elements we see here, usually there's going to be a max of plus or minus 1. All right. We would not often see charges greater than that in organic chemistry, unless we're looking at traditional inorganic type compounds. Okay, structures with single bonds. We'll get to that. How are we doing? Let's see. Common bonding, standard bonding. Let's go back here. I usually ask back over here, tellurium, uh, 128. All right. How many protons? Well, the periodic table tells us that the atomic number of tellurium is 52. So that's the number of protons. That would be the subscript. Neutrons is the difference between these two numbers. What would that be? 50 plus 26, 76? Is that 128? 76 neutrons for that isotope. And then electrons equals, well, if it's neutral, it should be 52. All right. Basically, make sure you can expand this discussion out to any element in the periodic table. And over here, I tried to expand this out by saying that underneath these we have the same standard bonding, but we do have some cases where we can have different bonding. All right. For sulfur, here we have an octet, standard bonding, but here we have something different. All right. You know, I think I'll end this first video here. And the next video will pick up with structures with single bonds, etc. on down the line. Although maybe let's do one real quick. Let's do the first one. But at this point, I want you to be looking ahead. All right. Now, if we were doing in traditional class, I want you to look ahead and be prepared for this discussion during next class period. Okay. In a video-only format, you should still be prepared, but since you will have more time to watch each video, it'll be a touch less critical. But certainly, if you're coming to class, you want to be prepared for the discussion to pick up at this point. And that's how my outlines are meant to serve you there. Okay, and you can even try some of these structures. The idea here is to put together a structure for a formula with CH4O. Let's do that here as we end this video. CH4O. Okay, and then you can be thinking about this before you watch the next video. How can we put together a structure here? Well, the first thing I recommend is how many valence electrons are we dealing with? Okay. Because Lewis structures, actually, we didn't really point it out, shows all valence electrons, either as covalent bonds or lone pairs. So if you want to show all valence electrons, wouldn't it be a good idea to know how many we're dealing with? Well, carbon has 4. Each H has 4, so that's 4 plus 4. And the oxygen has 6. That equals 14. So when we get through, we need to have that many valence electrons shown in our Lewis structure. Okay. Now, because hydrogen only makes one bond, it's always going to be on the periphery, the outside. It doesn't make multiple bonds. It can't be in the center. So, my first recommendation is to bond the heavy atoms first. And heavy atom is a term for non-hydrogen. So let's bond the carbon and the oxygen first. All right. Now that's 2 electrons right there, 2 valence electrons. My next recommendation is to place the hydrogens around carbon to fill the octet of carbon. All right. Usually that's what you want to do, hydrogens on carbon. Now there will be exceptions. But let's start by, and how many H's can we put around the carbon? Well, the answer is 3, because standard bonding for carbon is 4 bonds and 0 lone pairs, and that's what we have here. But we have one more hydrogen, and where would you like to put it? Well, certainly you don't want to make a 5th bond to carbon. It only has 4 valence orbitals. It can only hold 8 valence electrons. It is impossible to make another bond. The other H needs to go on the oxygen. So really, if you follow some basic principles, things start just falling together. Now, how many valence electrons have we shown? 2, 4, 6, 8, 10. We need to show 4 more. That would be 2 lone pairs. Well, guess what? If we put 2 lone pairs on oxygen, to satisfy standard bonding for oxygen, right? We now have 14 valence electrons. Standard bonding for carbon, standard bonding for oxygen, and we have a good structure. All right. Now I think this is probably the only structure you can come up with. But if you try the next one, using the same principles I recommended here, you'll see that you'll come up with isomers, 2 different possibilities. Let's finish this up. If we show this condensed, it'd be CH3OH. Now let's compare these two. This is just pure formula. A lot of times you'll see this written like this because it gives you some structural information. It's a CH3 group and then an OH group. And this is methanol. So 1 carbon alcohol. And if you ever see methanol written sort of typed out like this, it will always be typed out like this here. That's just devoid of any useful information. Although it is the actual formula. Okay, so we came up with a structure. I'll end this video here and ask you to try the next ones on your own a little bit, and we'll go through these and we'll see compounds that have double bonds and triple bonds. We'll bring in a nitrogen here, degrees of unsaturation, and we'll continue along this handout. Okay guys, this is our first lecture, trying to get us going here with some review and putting together some structures. Ultimately, we're going to want to put together larger structures, such as from a formula like this here. All right. And we'll continue on. Okay, guys, till next time.